Okay, good afternoon. Today we are going to start the bonding in octahedral complexes. In last lecture we have discussed the trigonal bipyramidal means DsP3 hybridization. Today we are going to start the bonding in octahedral complexes. That means there is a DsP3 or sp3d2 D2sp3 or sp3d2 hybridization. So D2sp3 hybridization complexes are inner orbital complexes, while the complexes which having the sp3d2 hybridization called as outer orbital complexes. So here we are going to discuss first D2sp3 hybridization, inner orbital complexes. Basically this type of complexes use inner d means n minus 1 d orbital, and here dx square y square and d z square, these two orbitals are used by the central metal ion, and there is a 1 s n s then np. So 2 n minus 1 d orbital, that means dx square y square and dz square are used, ns is used and np's are used. How many np? 3 np. Okay, so this 2 means d2 then s then p, that means d2 sp3 hybridization. So this is the example is given to you. CONH3 6 3 plus means hexaamine cobalt third is the complex. You will know well how we start the explanation. First of all, we write the electronic configuration. Okay, so 27 is the atomic number and electronic configuration is AR 18 plus 2 20 and remaining 7 is here. So 3d7 4s2 is the electronic configuration. Here cobalt has oxidation state. There is a plus 3 oxidation state, that means there is a 24 electrons. So we write the electronic configuration as a AR 3d6 4s1 4s0. 3d6 4s0 is the electronic configuration. Then once we write the electronic configuration, we represent the electronic configuration in the form of orbital form. So here electronic configuration of CO3 plus in a ground state. So we draw the first 3d orbital, then 1 4s, then 3 4p, then 3 4p. So here how many electrons in D? There are 6 electrons. So 1 2 3 4 5 and 6. There is no electron in 4s and 4p. Once we write the electronic configuration in ground state, then we observe how the D2sp2 3 or sp3d2 is possible. So is it the 2 d orbitals are empty? If yes, then undergoes D2sp3 hybridization. If not, then use next d, that time sp3d2 is used. So here there are 4 unpaired electrons in 3d orbital. So these 4 electrons are pair up. NH3 is a stronger ligand which forces to that electrons to make a pair itself. Once the pairing energy is supplied by the ligand, it is a strong ligand. So what happens when it goes to excited state? The electrons are pair up. Once these two pair here, the last two are becomes empty and that are used or available to undergoes D2sp3 hybridization. So here we write electronic configuration of CO3 plus in excited state. So on excited state there is a 3d 4s 4p. So once these are pair, all are pair in first three d orbitals. Next twos are empty, these are d x square y square and d z square. So the ion undergoes d2 sp3 hybridization, d2 sp3 hybridization, and then we finally write the electronic presentation for the complex. So these are 3D, and it is a set of next 5 2D, 1s and 3p. That means it is d2 sp3 hybrid orbital, and here the 3 electrons of cobalt in inner orbitals and the electrons which are coming from so electrons from 6 NH3 molecule, electron from 6 NH3 molecules. So this is the hybridization or representation of CONH3 3 plus. So here there is no unpaired electron. That means it is the diamagnetic and magnetic moment is 0. Complex shows D2sp3 hybridization. That means it is the octahedral geometry. So we can draw the structure here. Okay, is the octahedral. Simply you connect this one so it is the octahedral geometry. So you can write the explanation which is given in book, as well as just using this picture you can explain in your own words. So in CONH3 3 plus complex ion, the central ion CO3 plus has 3d6 4s0 electronic configuration. There are 4 unpaired electrons in 3d which are pair up and make a 2 empty d orbital which undergoes d2sp3 hybridization and form 6 d2sp3 hybrid orbital. The 6 d2sp3 hybrid orbitals are overlapped with the atomic orbital of 6 NH3 molecules and form 6 CONH3 bonds. There is no unpaired electron. That means the complex has 0 magnetic moment and diamagnetic in property. The D2sp3 hybridization suggests the octahedral geometry. So this is all about the first example. Okay, we're going to discuss the one more example is FeCN6 3 minus. So second is FeCN6 3 minus. FeCN6 3 minus. Okay. So first of all write the electronic configuration of AP26. Then it is the AR 3D 4s. There is a 3D2 and 4s2 3D6. Okay. So what is the oxidation state here? There is a -3, here is a -6, so here is a X, so X is equal to +3. That means Fe present in +3 oxidation state. That means there is a 23 electrons. So Ar 3D 5 4s 0. 2 electron loss from Okay, 2 electron lost from 4s and 1 electron lost from 3d. So D5 is the system. So electronic configuration of Fe3 plus ion in ground state. In a ground state. So there is a 3d, 4s, 4p. Okay, 3d, 4s and 4p. D having 6 electrons. Sorry, 5 electrons. One is already lost. So D having the 5 electrons. There is no electron in S. There is no electron in P. So when it undergoes, so what happened here? There is a 5 unpaired electrons to make a 2 empty orbitals. It is possible, yes, it is possible. And there is a ligand, who is ligand? Cn is ligand. It is very stronger in nature. So it provide the driving force, it provide the pairing force, or it provide the pairing energy. So the electrons are paired here. So this electron comes here, this electrons comes here. It is a single electron. Okay, there is no need of pairing. So 2 orbitals becomes empty. So D2sp3 is possible. So here electronic configuration of Fe3 plus ion in excited state. So in the excited state there is a 3d. So 2 orbitals are empty, the 4s is empty, then 3 4p's are empty, and again undergoes D2sp3 hybridization. It undergoes D2sp3 hybridization. So in a complex ApCN6 3 minus, here these 3d, only 3 orbitals are here, 3d, and with containing one single electron is here, and this is a set of 6 orbitals, and we called so we can use the electrons in the form of cross. So here electrons from 6 Cn minus, okay, and 3d containing 5 electrons. So there is a 1 unpaired electron. That means the magnetic moment has 1.8, means actually it is a 1.72 to 1.7 to 1.8, between the 1.7 to 1.8. So here mu is equal to 1.8 Bohr magneton. Nature is paramagnetic, and the hybridization suggests the octahedral geometry. That means here Fe Cn, 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 Cn. So this is the octahedral geometry ApCN6 3 minus. So this way you can solve. There is a number of problems which are given, some other examples are given. So the one unpaired electron shows 1.73 Bohr magneton is the magnetic moment, but actually when we observe, when we calculate experimentally, it is a 2.3. There is a large differences in that case. It is the 2.3, but maximum complexes shows the experimental and calculated value comparable. So in that case only the value is more difference. So this is all about the D2sp3 hybridization. We're going to discuss one more example. The other examples, CrCN6 3 minus, CrCN6 3 minus. CrCN6 3 minus. and the remaining you can you solve as a homework. So, chromium, atomic number 24, electronic configuration AR 3D 4s 3D 5 4s1. It is an anomalous electronic configuration 3D 5 4s 1. So what is oxidation state? Chromium present here oxidation state plus 3. That means 21 electrons. So here AR 4s 0, 1 lost from 4s and 2 lost from this one. So the remaining is 3d3. So we can represent the electronic configuration in the form of orbital. So electronic configuration of Cr3 plus ion in ground state. So here we draw first 5d orbitals, 3d, then 4s, then 4p. Okay, so when we put the electrons in 3d, there are 3 electrons. Already there is a 2 empty orbitals. So that means there is a no need of excitations. We can directly write. So it undergoes which hybridization? D2sp3 hybridization. D2sp3 hybridization. You can simple write the complex CN6 3 minus. So these 3's remains here 3D, and this is a set of 6 orbitals. And we call D2sp3 hybrid orbital. D2sp3 hybrid orbital. So there are 3 electrons here, and the remaining 6 orbitals containing 12 electrons from the 6 Cn minus. So electrons from 6 Cn minus. Electron from 6 Cn minus. There is a 3 ampere electrons. So if there is a 3 ampere electrons, the value of magnetic moment is, it is a 3.87 Bohr magneton. It is a 3.87 Bohr magneton. It is a paramagnetic in nature. It is a 3.8 to 3.9 something, you can calculate, okay. And the structure is so you can simple write the explanation. In Cr-Cn6 3 plus 3 minus complex ion, the central ion means Cr3 plus has the 3d3 4s electronic configuration. There are 3 unpaired electrons in 3d orbital and the 2 orbitals are empty. That means it undergoes D2sp3 hybridization, and there are 3 unpaired electron shows the magnetic moment 3.87 Bohr magneton, and it is in a paramagnetic in nature. The D2sp3 hybridization suggests octahedral geometry. So this is all about the inner orbital complexes. There are number of inner orbital complexes you can use or you can solve this way. So here we are going to discuss the second type of hybridization is it is a B type sp3d2 hybridization. sp3d2 hybridization. That means use the next d empty orbital, nth d orbital. So here it is the outer d orbital complexes. Again there are 2 orbitals which are used here, and the 2 orbitals are again same. It is a dx square y square and dz square. Both are used, but the difference is here. Here is the nd is used, but in that case Ns, Np and Nd orbitals are used. Ns, Np and Nd means all having same principal quantum number, but in inner d orbital complexes The principal quantum number of D is n minus 1 because D is anti-penultimate. Sorry, it is a penultimate, not an anti-penultimate. F is anti-penultimate. Okay, so we're going to discuss some examples of sp3d2, and the first example is Fe F6 3 minus. Okay, Fe 3 minus. And when we discuss this one, after we explain the bonding, then we compare this one with the one of the example of Fe. Why this happen, we are going to discuss. Okay, it is again the failure of valence bond theory. Okay, first of all we discuss here Fe atomic number 26 and electronic configuration is Ar 3d 4s2 3d6. What is the oxidation state? Plus 3 is the oxidation state of Fe in given complex. So here Fe3 plus has 23 electrons. That means here Ar 3d5 4s0. 3d5 4s0. When we plot the orbital representation, when we draw the orbital representation, it means electronic configuration of Fe3 plus ion in ground state, then here is a 3d, then 4s and then 4p. Okay, नंतर काय घेतलं 4p घेतला. आता बघा how many electrons? 5 electrons. 1 2 3 4 5. So same as Fe, when which this example we discussed earlier, the example is FeCN6. Okay, so in FeCN6 what happened, we pair up these 5 unpaired electron and we make the 2 empty orbitals here. That orbitals undergoes D2sp3 hybridization. But here the orbitals are not, means the unpaired electrons are not a pair up, they remains, and the complex or center ion use next empty d orbital. So on excited state the pairing is not possible, not happen, because pairing energy which is supplied from the ligand is not given, and that's why pairing of electron is not happen, means all the electrons remains unpaired because of the magnetic moment will indicate there is a 5.90 is Bohr magneton is the magnetic moment. That means there is a 5 unpaired electron present in the complex. If we pair up, there is only one electron is available and we expect the 1.7 to 1.8 is the magnetic moment, but actually the experimental and observed value is there is a 5.9. That means there is a 5 unpaired electron. That's why VBT use the next one. But there is no any evidence, no any explanation is given in the case of same metal ion, same oxidation state, but ligands are different. In first case Cn minus is there, in that given case is the F is given, means the ligands are changed only, but one shows inner orbital complex, another shows outer orbital complex. So that's why this is a failure of the valence bond theory. Valence bond theory only regarding the metal, not about the ligand, nature of ligand. If ligand is changed, what is the effect on the bonding will not given by the valence bond theory. So that's why the strong and weak ligand are classified. The next theory is the crystal field theory. But here the nature of ligand is not explained by the valence bond theory, and this is another failure कि some metal having same oxidation state, but for one ligand shows inner orbital complex, for another ligand shows outer orbital complex. And this is the failure not explained by the VBT well. So this is the limitations of VBT. So here we are going to discuss electronic configuration of Fe3 plus ion in excited state. So here used 4D. So 4s, 4p, 4d means principal quantum number is same. That means here nth d orbital. So these 5 remains here, and here use sp3d2 hybridization. sp3d2 hybridization. Okay. So for this complex Fe F6 3 minus, this 5 remains. There is a 3D 1 2 3 4 5 and the set of 6 is here. We call it sp3d2 hybrid orbitals. So here electrons from 6f minus, electrons from 6f minus, and the remaining 4 Ds are there. These are the vacant. So the magnetic moment of complex is, it is very highly paramagnetic and the value is given okay, you can calculate. It is the mu is equal to 5.92 Bohr magneton. It is highly paramagnetic, highly paramagnetic, and you can draw the structure of this one. So Fe, F, F, F. Okay, so this is all about the Fe-F6. The last example is given NiNH36. NiNH36, you can solve, you can try it. I just draw the electronic representation. You write in detail in notebook. So NiNH36 3 plus. Okay, NiNH36 2 plus, sorry, 2 plus. Okay, so Ni, atomic number 28. Here is the Ar, 3D, 4s, 2, 3D, 8. 8 electrons in 3D. What is the oxidation state? Plus 2 oxidation state. That means 26 electrons are remaining and both electron lost from 4s. So Ar, 3D, 8, 4s, 0. When you draw in ground state configuration, then 3D 1, 2, 3, 4, 5, 6, 7, 8. Then 4s, then 4p. Okay, look at here. If there is a pairing or not. If pairing, one pairing is there, only one orbital is empty, means pairing is not possible. Pairing energy असली तरी pairing झाली तरी काय उपयोग नाही, कारण की हा इलेक्ट्रॉन इथं आला तर एकच एम्प्टी होणार. सो हिअर इन दॅट केस लिगँड स्ट्रॉंग जरी असेल NH3, तो पेअरिंग जरी केली तरी तो दोन एम्प्टी करू शकत नाही, म्हणून हेअर यूज नेक्स्ट डी ऑर्बिटल. लिगँड NH3 आहे, स्ट्रॉंग आहे, पण त्याने पेअरिंग केलीही तर काय होईल, इथं पेअरिंग होईल आणि एकच एम्प्टी होईल. आपल्याला किती लागतं एम्प्टी? दोन एम्प्टी लागतं, कारण की कोऑर्डिनेशन नंबर 6 कॉम्प्लेक्स आहे. सो देयर इज नो पेअरिंग, यूज नेक्स्ट डी. सो एक्साइटेड स्टेट, थ्री डी, 4s, 4p, 4d. Okay, so used this one. So electrons from 3D remains. So here sp3d2 hybridization, sp3d2 hybridization, and you can write for the complex NiNH36 2 plus this is a set of 6. Okay, you call it sp3d2 hybrid, and you can represent the electrons here. So electrons from 6 NH3. Electrons from 6 NH3. So there are two unpaired, how many unpaired electrons? Two unpaired electrons. The value is 2.92. So mu is equal to 2.92 or 2.87 something Bohr magneton. It is paramagnetic. It is in a paramagnetic and the structure is octahedral. So you write all the examples in detail which is given in book, explain in your own words and try to understand. It is very easier. On this step you decide is it the complex is outer or inner. So that time important key points are look at ligand. If there is a halide is weak in ligand, so mostly halide is not pair up the electrons, but NH3, Cn, CO, these are the strong ligands which pair up the orbitals. When pair up is happen, if after pairing, is it though two orbitals are empty or not? In that case, the pairing is not important because there is no effect on these condition because if pairing is happen, pairing झाली तरी सुद्धा आपल्याला दोन लागते पण एकच होते म्हणून इथे pairing होणारच नाही. So this is all about the today's we're going to discuss in next lecture inner and outer orbital complexes and after that there is a electroneutrality principle. Okay, so read it before the lecture, electroneutrality principle and inner and outer orbital complexes. We stop here.